All right, here's a quick look at how to basically go about dealing with limits. Now, we actually going to start out with a couple problems that will be familiar. We've done this part before. So these are dirty dozen. That's DD you're seeing on there next to each of those problems. Dirty dozen. We have x going to infinity and negative infinity. And the idea to evaluate those limits, remember, a limit, the output is a height, like what output value does it go to? So when I look at these, dirty dozen means you should be able to graph these. You know what these functions look like. So you're going to evaluate them graphically. It says use your calculator, but you know these. Don't worry about what the calculator tells you. If you go about each of these and draw a little basic kind of graph, I mean nothing fancy, just your kind of fundamental basic graph of a quartic, a linear function, a cubic, and a quadratic, noticing whether they're positive or negative, etc., then you should be able to say, hey, as x goes to infinity or negative infinity, I know these values. And so you can put those in there. Those are corresponding values that go with it. The first one, the quadratic, as you go to the right, positive infinity, the function goes to a height of infinity. The limit on number 2 is you go to negative infinity, your function goes down, down, down to negative infinity. And number 3 is x goes to negative infinity off to the left. Your function's going up, 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 up to positive infinity. And in number 4 there, as the limit as x goes to infinity, that's to the right. The function in both cases it goes to negative infinity. Pause as you need to take all that in, and then start it up again, and we'll go to the next part. So now, down below, what we're going to do in 7 and 8, this is 7 and 8 is also familiar territory. Do you remember when we had to analyze the degrees of the numerator and denominator? That's 7 and 8 if you're doing rational functions, like those fractional functions, and you go x to infinity or negative infinity. What we notice is that, remember how we looked at this? It was all about the degree of the numerator and denominator. If the larger degree was in the denominator, this went to 0 as x got really large because you ended up with a fraction with a large denominator. And if they had the same degree, then it was the ratio of the coefficients out front, 4 over 1. And so this had a value of 4. So that's the old stuff that we did once upon a time that you want to know again. What would be new, 5 and 6 are all about actually graphing these. These are actually 1 over x functions that we've transformed in number 5 and 6. And you don't want to look at the graph and say, as I approach the various values from left and right, you have to look for that little plus or minus, what direction you're coming from. Where does the function go? So here's number 5. It's like a taller 1 over x function to the right 2. And if I approach 2 from the right-hand side, coming in from the right, you can see it's going to infinity. If I look at the other function and I simplify it a little bit, if I factor out a 2 in the denominator and then rewrite that a little bit, you can see it's just a taller 1 over x function that's kind of shifted to the left 4. And this one says as you approach negative 4 from the right, or from the negative side, from the left-hand side, that's what that negative means. So I've got a yellow arrow showing coming in from the left. That means you're going to negative infinity, and that's the value of that limit. So remember, it's just sliding in from a particular direction. You need to know how to graph these basic functions. So really these are, the first 6 are all about just graphing dirty dozen known functions and saying where's it going. And then the last 2 there are that larger denominator, those rational fraction limits rules that we learned. All right, pause if you need to take a look at that, back up, and so on. I'm going to go into the next section. Okay, so down below, there are times when you can evaluate a limit just by putting in the limit value directly. Really, it's anytime you have a polynomial, any kind of function where there's really no restrictions, so any continuous function, one that doesn't have any asymptotes, then you can always just sub in the value of the limit directly. So it's kind of silly to say here, number 9 is a quadratic. It would graph a parabola. As x approaches 5, what is the value or the height of the function? And you might be saying, well, why don't I just put 5 in? And you'd be right. In a continuous function that's smooth, then with no breaks in it, there's not a lot of value to a limit in that sense. You want to just say, oh yeah, I just put that in directly. So that's what I've done here in number 9. So continuous functions, you can do that. You just get 66. Okay. Next couple of the same thing. You're just going to put those values directly into those functions. I'll let you do those on your own. You don't need me to work through that. Okay, so do that on your own time here pretty shortly. On the flip side, number 13 through 16 here, that's a page turn for me, not for you. But you'll notice that you can simplify for these two reasons. Either you want to graph this thing to evaluate graphically like we did above, or you can find out that, you know what, that value of the limit, you can sub it in directly. Before, and sometimes we use limits in situations where you can't put that number in directly, like there's an asymptote or a hole in that particular location. So what we do is limits allow us to get really close to a place that doesn't actually exist, like a break in the graph, and actually figure out what the function is doing there. So, but if it's continuous, we don't have that issue. So let me show you what that looks like in case that explanation didn't make any sense to you. So here's 13. So right now, if I put -2 into number 13 directly, that limit value, I'd divide by 0 and this wouldn't work. So this is a great time to have a limit. Well, to go about evaluating this limit, one thing we can do is simplify it a little bit, and we may be able to sub that -2 in there still yet after simplifying. That may be possible. Sometimes you can do a little algebra pizzazz in there, and you can get to a place where you can just sub that value of the limit in. This is one of those cases. I can also graph this very easily and evaluate it that way with a graphing calculator. That's cool too. But notice I factored both the top and bottom. We're going to have a cancellation, and we have a hole at x equals -2. Well, that was the whole issue to begin with. I couldn't put -2 into this directly. I couldn't sub it into because it would cause the dividing by 0. Well, I just canceled that x plus 2 that would have caused that dividing by 0. So I'm good to go. I can actually graph this. I know what this looks like, 2 over x minus 2, which is also helpful. That simplifying allowed me to graph this without a calculator. But also I can put that -2 in directly, and I can find out what the height is. I can actually tell you where I'm going, where that function is. I get 2 over -4, -1/2. The height as x approaches -2 is -1/2. You can see that on the graph. You could evaluate that with the trace function, among other things on your calculator too. So that's the value of that limit. Okay, we're going to talk about the rest of these, but you've got the big tools in your pocket right now. I'm going to flip and get to that limit gateway. I want to do some of these with you so I can kind of get the ball rolling on some of the same concepts we just talked about and let you finish everything else on your own. So let's pick up where we left off. Same idea is, so if we're going to look at this, let's go to that gateway, the limit gateway that I have for you guys today that's printed off. We want to factor this expression because we're going to do limits on this rational function. So if you can factor a rational function, do so. So I've done the denominator factors. Do you notice that we can go ahead and cancel those denominator numerator x minus 5 factors? It means there's a hole at x equals 5. So and then the leftover 1 over x plus 2 is very graphable. We know there's a vertical asymptote at -2, and it's like a 1 over x graph. One thing we need to add, though, to our graph is that hole at x equals 5. You need to indicate that. It's really important in limits to indicate that hole. You have to give that in that graph. The next thing is now we can do evaluating the limit at the various places you see in part B. So for instance, if I want to do the limit at x as x approaches 5 from the right, in that first part, the idea is coming in from the right-hand side. What's the value, the height of that function as you approach 5 from the right? Well, the thing is, remember, if you can put that value in directly, direct substitution, you go for it. And we canceled the x minus 5 factors, the reason we couldn't put 5 in directly before, and now we can. So in that 1 over x plus 2, you just directly substitute the limit value. So you always, if you can substitute directly, do it. It's the easiest way to evaluate a limit if it's an option to you. So we get 1/7, and it makes sense looking at the graph, or if you traced it and used your calculator to see you'd get 1/7. And same goes from as x approaches 5 from the left-hand side is the same height. There's a hole there. It doesn't exist. This is where a limit's important because we can't, technically in our original function, there is a hole there. So we're just getting really close, infinitely close to the x equals 5. And we're seeing that the graph goes to a height of 1/7. So we know the hole is at a height of 1/7 exactly. That's what that's kind of saying. And because these one-sided limits agree, the left and the right-hand limits agree, it's a really important calculus concept. If the limits agree on either side, then we say the limit exists. Okay, so there is a definitive, and we call it the general limit. As x approaches 5, which is a statement about both sides, as you approach 5 in general, then the value of this particular limit at x equals 5 as x approaches 5 is 1/7, and the limits agree. Now we'll have a situation here in a minute where the one-sided limits don't agree, and therefore the limit does not exist, which harkens the old quote from the movie, of course, Mean Girls. So limit as x approaches -2 from the right. If you go to that asymptote, if you go in from the right, you go to positive infinity. From the left, you go into negative infinity. And then that means those are one-sided limits approaching the same value of -2. They don't agree. They're two different numbers. So this is a situation where the limit does not exist. So in general, if the one-sided limits do not agree, then the limit does not exist. Okay, so that's the big quote that you want to take with you. All right, we're going to go ahead and this will be paused. This is part 1 of getting limits underway. I'm going to let you guys evaluate the rest. I'll give you another video to help you with part 2 to continue your work.